Okay, we are going to talk about 3.6 part 2. Math. We're going to start with annual percentage yield. That's abbreviated APY. And that is when I'm compounding more than once a year, what would be my rate if I compounded it once a year? Okay, so if I compound more than once a year, it's going to be a little bit higher return than if I compound every year. The annual percentage yield is what's the amount that I get if I compound once per year. And so example 6 says Ursula invests 2,000 with Crabtree Bank at 5.15% annual interest. Compounded quarterly, what is the equivalent APY? So they set it up 1 plus R to the first, essentially. And then on the other side, we do it with our rate of 0.0515. Quarterly is 4 for the N to the 4 times 1. Again, I'm using this equation. The N was 4. P is my principal initial amount. My other side, N is 1, so I didn't bother writing it on the left side of the equation here. And this really nice thing happens here. And I usually don't even bother to write it. But my 2,000, my amount doesn't matter. It just divides out. And I'm left with 1 plus R, I don't need to the first power, equals 1 plus 0.0515 over 4 to the 4th. So now I just go to my calculator and I stick in this value on the right. I get 1.0525 equals 1 plus R. My rate is 0.0525. I subtract 1 from both sides here, or my APY is 5.25%. Instead of 5.15%, I'm now getting an extra 10% by compounding it quarterly. Usually when I'm setting up this equation, I start right here at that line. I don't put in the amount because it cancels out no matter what it is. So we're going to compare APYs on a couple of different accounts. I have which investment is more attractive, one that pays 8.75 compounded quarterly, or the one that pays 8.7 compounded monthly. Okay. So looking at R1 is going to be my APY for my 8.75. .0875 compounded quarterly. And then over here on the right, I'm going to do R2, which is going to be my 8.7 compounded monthly. So I'm using essentially that same line from before. And I get 1 plus R1 equals 1.09. Let's make that neater. 0.9041. R1 is 0.09041. I'm keeping a lot of decimals because I think these are going to be rather close. This is example 7 in the book too. Okay, so R2, when I stick this right side in, I get 0.09055. So R2 equals 0.09. No, I get 1.09055 equals 0.09055. The second one is better. 8.7% compounded monthly is slightly better than 8.75 compounded quarterly. They're pretty close though. So, but I would always choose the higher one. Might as well. It's a little bit better rate. Okay. So that's how to calculate annual percentage yield. Now, most interest that we have and things, we don't make a deposit in once or let it sit and grow until we pay it off once. We do things every month or every quarter. So if you're saving for retirement, you probably don't want to make a deposit once and then let it sit and never add to it. Usually what you want to do is add to it, usually either every month or every year or every quarter. So we get what we call an annuity. And again, to make these calculations simple, we add the same amount every time. Okay. So an annuity is a sequence of equal periodic payments. An annuity is ordinary if the deposits are made at the end of each period at the same time the interest is posted in the account. Okay. So again, I'm making it at the end of the period and interest is accumulated then. So not always perfectly done. These things are calculated live, but you can plan ahead using a couple of different formulas. And these are in your formula packet under exponentials. I wrote them out a little bit more detailed than the book. So FV stands for future value. And I wrote them out in basically the same things we've been using. R is my payment amount. So R is my payments. I don't know why they call it R this time, but I used that in the formula packet. That's the one that's new. And this will go across both. Amount is 2M's, I think. I'm going to use brackets instead of using double parentheses here. Write this down in a notebook because we're going to reference it a few times and it might not all fit on one page. Or have your formula sheet next to you. It's on the equation form sheet under exponentials. So this is mine for future value for what I'm going to have after X amount of years. Say I deposit every month $200 for 20 years to save for retirement. I don't know if that's enough or not, but kind of the idea. Present value would be like I took a loan on my house. What's it going to take to pay it off? So I put that on the wrong side. This on the present value is a negative exponent on t. So a couple of things have switched around. The equations are pretty similar. But okay, we're going to look at example 8 here. So at the end of each quarter, Emily makes a $500 payment into Langhand Mutual Fund. If her investment pays 7.8%, so I'm going to start by writing down what I know, $500 each quarter, and little r is 0.0788. So that's my rate. And asks what her investment will be worth in 20 years. Oh, wait, no, time is 20. Future value is my unknown. So this is a pretty straightforward one. I'm just going to plug into the equation. And then I'll actually show you plugging this one into the calculator. 500 parentheses brackets 1 plus 0.788. Let's make those a little neater. Over 4 to the 4 times 20. Okay, let's go to the calculator. I'm going to plug in exactly that. So I'm going to start with, I'm going to use a lot of fraction bars. That was not what I wanted to hit. Okay. 500 times, and I kind of just am stuck with double parentheses here. 1 plus 0.0788. I'm just going to use a division here instead of a double fraction. To the power of 4 times 20, I can just multiply and get 80. I do need the -1 before I close my parentheses. And then my denominator is 0.0788 divided by 4. And after 20 years, she's going to have $95,483. Which is pretty good. She deposited, if I want to keep track of what she deposited $500 4 times a year for 20 years. So 500 times 4 times 20. She only deposited $40,000. She comes out at the end because of interest with 95,483. Now she'd have quite a bit more if she deposited that 400 or 40,000 at the beginning, but she gets interest on all of it as it goes in. So she's not getting interest on the last 20,000 until the last, well, pieces throughout the last 10 years. But none of that gets interest until it goes into the account, which it's still pretty good. If she did this, I'm going to enter it just with the equation just to see what it would be if she entered it all at once. And I expect it to be quite a bit more. Yeah, it's 190,000. Now, unfortunately, when you have this, you don't have $40,000 sitting to just throw in there unless you get almost twice as much. But she did make 45,000 extra in interest as she made these deposits. Even just going a little bit at a time for all these years. We're going to do a loan one. A loan is basically an annuity in reverse. We'll use this present value one. I'm going to skip ahead to a new page so I've got more space. This is example 9. Carlos purchases a new pickup for 18,500. What are the monthly payments for a 4-year loan with a $2,000 down payment if the annual interest rate is 2.9%? He got a great rate. This is example 9. So my present value, that's what I owe here, is not 1850. 18,500 is what he started with, but he put down a $2,000 down payment. So I'm going to subtract that off and get my present value to be 16,500. I know his rate is 0.029. We are looking at what are his monthly payments? That's R is going to be what I'm looking for. His payments. Oh, T is 4 years. He gets 4 years to pay this off. And if it's paid monthly, we're compounding monthly, N is going to be 12. Okay. So I stick it into my equation. My unknown here is R. 1 plus 0.029 over 12 to the 12 times 4. That's a dot, not a minus. Minus 1 over 0.029 times 12. I'm going to do a couple of things as I calculate as I go. But to solve this, I'm going to multiply both sides by my denominator. I'm just going to do that on my calculator here. Let's go back to red. Gives me 39.875 equals R. And I'm going to, everything in brackets is numbers, so I'm just going to do that. Oops. Okay, I've kept a lot of decimals on purpose. Now, when I do this on the calculator, now all I have to do is divide by and I just enter my 39.875, and I'm dividing by my previous answer, which gives me a lot of decimal points. 324, 61.612. I'm going to round that up to 62 because he's always got to pay. If he pays slightly over, then he'll actually be paid off in 4 years. So we're paying a 7/10 of a cent more, 8/10 of a cent, somewhere between 7 and 8/10 of a cent extra. So I get a different answer than they do. Oh, I screwed up. I missed something in my equation. This is a negative. That has to be a negative. So back up, we're going to have to I gotta change that value. Important not to miss the negative. Oh, I did multiple things wrong. This is not good. I did it like the other equation. It's 1 minus. And I guess 12 times 4 normally, but I'm gonna make that a little later. So again, my first step on the right was the same, giving me 39.875. And it gets rid of my denominator on the left when I multiply both sides by this. Okay. Now, when I do this part on the top, part in the brackets, and I do it correctly, I get this. I get a couple zeros, so I'm just going to leave off there. Now I can just divide by that 0.1094. And I get 364, and I'm going to round up. Always going to round up a cent. 364.49. You'll be a few cents less on your last payment. Great, nice. But this is what he's going to have to pay every month for 4 years or 48 months to pay off his loan.